All right, so these notes are going to be about chemical reactions. We are going to be learning about the 5 different types of chemical reactions and how we identify them. So there are 5 types of chemical reactions. They are synthesis reactions, decomposition reactions, single replacement reactions, double replacement reactions, and combustion reactions. When we get to our unit test, which will be when we come back after winter break, a little bit in, you'll need to be able to identify each of the different types, and we're going to talk about characteristics of each, and you'll get lots of practice before we get to that point. So how do we know that a chemical reaction has occurred? Well, one thing, these are some things that we can see. There's a temperature change, that could be an increase or a decrease in temperature. We get a color change. There's an odor that's present that wasn't there before, and we'll look as we get further into labs of how we appropriately smell a solution or a chemical. We can have gas bubbles or gas that's produced, and sometimes it kind of looks like steam coming off, or we see bubbles in the solution, or we have the appearance of a solid. Another word for that is a precipitate. And what you can also put in your notes, I'm going to go back to our slide here, is a precipitate. An abbreviation for precipitate is PPT. And so you might want to put that after precipitate in your notes. It'll be helpful later for you. And you might see it as an abbreviation on some of the work. It's also a lot quicker than writing precipitate on everything. Okay, so the first type we're going to talk about are synthesis reactions. So a synthesis reaction is, I'm just going to take off the pen here. Synthesis reaction is when we have 2 elements. So we have sodium here and chlorine. Chlorine is what's called a diatomic molecule. We haven't talked about those yet, but they're elements that when they naturally occur, they occur in pairs. They like to pair up. Makes sense. Chlorine only has 1 electron it's missing, so they share a pair of electrons, and then they're balanced and stable. And so we have 2 individual elements that combine to make a compound. Okay, so you're probably thinking, well, what do we need to write in our notebook? It is up to you. I have some students that just write the name of the type of reaction and then this equation down here, A plus B equals AB, indicating element plus element yields compound. Or you could write out this equation and then put this underneath, so indicating that this is your, excuse me, this is your A, this is your B, and this is your AB. You can draw the dots if you want to, but you certainly don't have to, okay? All right, I am just going to go back to the pointer. Here's an example of a synthesis reaction. Okay, so in this reaction, we have potassium. That's a silver piece down here. It's in the water. It's a solid. Then we have chlorine, which is a gas. When they are combined together, there's a reaction that occurs, and we get potassium chloride, which looks like a salt right here. Okay, so that's one type of chemical reaction. So then one of the questions I got asked a lot from the homework that we had is, what does the S and the AQ and the G mean? So on some of the equations, like back here, we have these letters that are behind, and what they indicate is what state it's in. So an S in a chemical equation signifies that we have a solid. If we have a G, we have a gas. If we have an AQ, that means aqueous, which means it's dissolved in water, and I'm going to come back and explain that in just a minute. And L means liquid. Typically, these are the state that they're in at room temperature. If you look at your periodic table, all the elements are colored. Their formula is based on their state of matter at room temperature, because that's usually when we're working with them, is at room temperature. Most of the elements in the periodic table are solids. But if I took a powdered solid and a powdered solid and I mix them together, a lot of times a chemical reaction isn't going to occur. I have to have them in a solution. So what that means, I have to take the solid and mix it with water and dissolve it. And so then we would call it aqueous. So aqueous just means we took the solid and we dissolved it in water so that we had to have a solution we can work with. So why do we need to note these? You're probably thinking, oh my gosh, do we have to write these on every single chemical equation we write? And the answer is no. But when we're looking at whether a chemical reaction occurred or not, sometimes we have elements that change phases in a reaction. So example I'll give you is sodium and chlorine. Sodium is a solid. Chlorine is a gas, but when they combine as a compound, it becomes a solid. So chlorine goes from being a gas to a solid, and that indicates that we had a chemical reaction that occurred. So that's why it's important. All right, so the next we have decomposition reaction. This is the exact opposite of a synthesis reaction. So we start with the compound and we break it down into the individual elements. So example, we have here sodium chloride, table salt, breaking apart into the chlorine and the sodium. So AB yields A plus B. So we have a compound equaling the element and the element. We're breaking it apart. Think about if something decomposes, it breaks down. We're taking a compound and breaking it down. Here's an example of a decomposition reaction. We have mercury oxide, which is a solid down here. If we heat it, this is an ionic compound and they need lots of heat to break bonds. We get liquid mercury and we get oxygen gas. The next type we have is what's called a single replacement reaction. And so with this, we have a compound, AB, and then we have an element, and we have partner switch. So these two switch places. The zinc bonds with the chlorine, and the copper ends up by itself as an element. Biggest thing we have to know here is that we're replacing with the same type. What do I mean by that? Copper's a metal, zinc is a metal, so they can replace each other. Chlorine is a non-metal, and so we want to make sure that we're replacing with what we have. So these two can switch places because they're both metals. If we had a non-metal over here, that could switch places with a chlorine, okay? Because this is an ionic compound, metal and a non-metal. Okay. All right, the next type is, so our single replacement reaction, we have lithium. That's this little piece here. We drop it in the water, bubbles, gases, and what we get is lithium hydroxide and hydrogen gas. All right, double replacements, really similar, except for now we're both trading partners. So the magnesium and oxygen are bonded, and they're going to switch partners. So that means the magnesium and the sulfur are going to combine, and the oxygen and the calcium are going to combine. We're just switching what we're bonded with. Okay, again, we have to make sure metal switches places with another metal, non-metal switches places with another non-metal. So essentially, we leave two where they are. They did that with the magnesium and calcium in this one, and we just switch the bottom. Or you could leave the bottom and switch the top, okay? You do not need to write this, but the authors talk about how this is like foiling in algebra. So the outer ions go together, okay? So like these will go together because that will give us a metal and a non-metal. And then these two will go together, non-metal, metal. Same thing here, metal, non-metal, metal, non-metal. Okay. Our last type are what are called combustion reactions. Combustion reactions are when a hydrocarbon reacts with oxygen gas. This is also called burning. In order to burn something, we need three things in the fire triangle. We need a fuel, which is our hydrocarbon. We need oxygen. And we need something to ignite the reaction, which is what creates our spark. So our fuel is our hydrocarbon. So for example, in our lab, we hook up our Bunsen burners, and when we turn the gas on, we have propane, that's our hydrocarbon. We have oxygen in the classroom, and then we use our striker to make a spark so that the hydrocarbon can burn. With combustion reactions in general, we have a hydrocarbon just means it's made of carbon and hydrogens that are bonded together. The X and the Y just tells us that this ratio can change. So like there's CH3 and CH4. C8, H18. So there's all different hydrocarbons. So some familiar ones you might know: propane, methane, butane, octane. Those are all hydrocarbons. Okay. So we have a hydrocarbon plus oxygen yields carbon dioxide and water. When we're trying to identify these, the products are always carbon dioxide and water. That's all we get for a product. Okay, that's all we're left with. So if we get carbon dioxide and water, we know we have a combustion reaction. Combustion is what we use to heat our homes, run our cars. Octane is what's in gasoline, and it's this hydrocarbon. And so that is our last type of reaction. There's just a couple more things that I wanted to share with you, and I'm going to draw on here. And it was something I would draw in my notes, and you can draw it on this equation or you can draw it somewhere else. But I want to explain the parts of a chemical equation. So on this side, these elements are what we call our reactants. And then on this side, these are the products. So how I always think of it is, this is what's produced. This is what reacts to get our product, okay? This arrow, it's kind of like the equal sign in math, and we would say it's yields is what it means. So if I were going to say this as a sentence, let's add this hydrocarbon in. I'd say octane plus oxygen yields carbon dioxide and water, or plus water, either way. So this arrow means yields. There are also some symbols that can go on top of the arrow to indicate more detail of what's happening, and we'll talk about those a little bit later as we go through reactions. But those are the notes for today on chemical reactions. Let me know if you have any questions. Thanks.